Hello, everyone. Welcome back to Sustainability Issues in Energy. I hope you've been enjoying this lecture series. Just a reminder, if you want to get notifications and keep watching these videos, if you've been enjoying them, please go ahead and subscribe to the channel. I've been putting out a lecture about once a week and hope to keep up that frequency throughout the summer as the course materials come together. Today, we're going to be talking about carbon utilization. So remember, CCUS, carbon capture, utilization, and storage. So today we'll be on the U side. So the general principle here is that let's imagine that you've gone through some sort of carbon capture process, and we've spent the last couple of lectures talking about those. Now, what are you going to do with it? So you can either use it for something, or you can dispose of it. And so today we're going to talk about the using it for something, the utilization aspect of this. Here's a nice figure from the US Department of Energy showing the 4 components of carbon utilization, or the 4 ways that it's generally utilized. So we'll talk about algae, mineralization, conversion, and then services, and specifically using CO2 as a working fluid. So algae uptake is a really promising way of using carbon dioxide to make new materials. So this is a aerial photograph of a large-scale algae farm in Columbus, New Mexico. It's in far southern New Mexico. And it's run by this company called Qualitas. They're actually a supplement making, dietary supplement making company. But they currently run 2 of these farms. One is this one here in New Mexico. The other one is here in Texas, in Imperial, Texas, which is way out in West Texas. And they've generally been using them to make omega-3 fatty acid supplements, but they're now looking at getting into the meat substitute business using some of the amino acids that are generated by the algae. So there's a lot you can do with these things. The algae, I'm going to be honest, it looks kind of gross, but there's a lot of good stuff in here. So the general principle that we're looking at here is that algae takes in carbon dioxide, sunlight, and water, and it produces oxygen and then biomass, which is actually, just the stuff that the algae is made up of. So it's a fairly straightforward process. And when you look at you can capture that oxygen and use it for something, although, it's always good to let that just go back into the atmosphere. But the biomass can be used for a lot of different things. So when we compare algae biomass production to terrestrial biomass production, and what I'm talking about there is like things like farming waste products like corn stover and seed hulls and that sort of thing, comparing the 2 types of biomass production. This is a nice comparison table from the DOE. Algae obviously grows in an aqueous medium, whereas terrestrial biomass has to grow in soil. Here's one of the big advantages of algae, is that it can grow in basically any type of water, including highly saline water. I don't know how many of you have had the pleasure of visiting Imperial, Texas. Back when I was worked for an oil field service company, based out of Midland, I drove through Imperial a fair amount. It suffers from a hydrogen sulfide problem because of the nearby oil and gas production infrastructure. So it doesn't smell the best, but it has extremely saline groundwater. And historically, there's actually been a lot of brine shrimp farming going on out there. You're kind of in the middle of the desert, but you can actually farm brine shrimp. And so it's also a good, candidate location for algae farming. Let's see, in terms of resources, algae use similar things to terrestrial biomass, but here's the thing, is that they, require a source of CO2. Obviously, terrestrial biomass just takes that up from the air, but the algae can, use a direct source to really enhance the growth. Let's see, some of the other differences is that you can harvest the algae much more frequently because it grows a lot faster. And then your biorefinery, so this is where you take the biomass and actually break it down and make chemicals out of it. That's generally done on site. Whereas terrestrial biomass, your farmer is going to come around and collect that waste product and then, send it somewhere else to be refined. And then the last thing is that, obviously, algae, you can recycle the water and you can recover up to 90% of the nutrients that are in that water for regrowth of new algae. Whereas terrestrial biomass production actually can be bad for the soil because you can lose nutrients through erosion and runoff. So there's some significant differences here, and algae has a big advantage. Now, what can you do with it? Well, like I said, the biomass can be, contains a lot of different chemicals, and it can be broken down and used to make new chemicals. And so everything from, biodiesel to bioethanol and biomethane. You can make biojet fuel. Let's see, what else? Bioplastics, biopesticides, food, so you can, protein substitutes, that sort of thing. Livestock feed, omega-3. So there's a lot of different things you can do with algae, and it's a really promising use of captured CO2 that then itself can be used to substitute for a lot of other different types of chemicals that might be problematic in terms of their production and use. Okay, let's talk about mineralization a little bit. So mineralization generally refers to concrete, this process called upcycling of concrete, which we'll talk about. You can use that to make building materials, and then various inorganic materials and precipitated carbonates that are used in materials like paint and that sort of thing that need these things. Okay, so upcycled concrete. I did a Google image search for upcycled concrete. This is what I found. You can use it for planting your succulents. You can use it for keeping your beverages cold. You can even use it for a fancy sleeping pod. I'm not sure how excited I would be about that, but hey, that's actually not what we're talking about. This is what upcycled concrete is. So this is a concrete manufacturing strategy that produces upcycled concrete and actually uses waste heat and CO2 from a power plant. So this is a pretty cool process if you can get this to work. So you take your raw materials here that you need to make concrete. So you take your slag and your fly ash and water, and those are made for making the cement paste. So you leach calcium out of the slag, and those of you who know about concrete manufacturing know that actually this process can produce a fair amount of CO2 in itself. So you could imagine capturing that along with the CO2 from the power plant waste stream and going over here with it. So anyway, you've got your slag and your fly ash, add water, and then your aggregate material, and then you've got your concrete down here. And so all of that uses waste heat coming out of the power plant. So then you've got your concrete and you extrude it to make, whatever it is you're going to make. Here's a beam being made in this case. And then what happens is you take excess CO2, either from the power plant waste stream, or I mentioned you could take it from the leaching as well. And you essentially stick that CO2 back into the concrete. Obviously, it's not that simple, but CO2 will react readily with concrete and get itself into the structure of the cement and actually generate a strong, stronger and more durable material than what you get with the initial process. So this is actually pretty cool. There's a number of different other mineralized products you can make as well. So there's a bunch of companies that have been looking at various types of mineralized products to make, concrete blocks and aggregate, roofing tiles, these upcycled concrete, soil amendment, that sort of thing. So these are the companies, this is what the technology is called. This is the technology readiness level here. So just to flash up what these numbers mean, a lot of these are kind of in the 6 to 7 range. So this is a scale is originally defined by NASA, but basically if you're at TRL 6 to 7, you've got a verified prototype system and integrated pilot system. TRL 9 is the highest level. That's you're proven in an operational environment. TRL 3 is proof of concept. So that's generally what we're looking at here. So you can carbonate olivine. We've talked about olivine before, and it can be used to make building materials. That's a bit of a less mature technology. But anyway, there's a lot of different mineralized products that you can get using carbon dioxide. Okay, let's talk a little bit about conversion. So you can use carbon dioxide to make something that's called syngas. This either can be used by combining methane with carbon dioxide, and then you get carbon monoxide plus hydrogen. You can also do that by combining water with carbon dioxide to get the same products over here. And so then this syngas is used in a refinery to build all kinds of different things, including ammonia, methanol, synthetic diesel, synthetic petroleum, all kinds of good industrial chemicals that we need. Now, the problem with this is that you need to split carbon dioxide in either water or methane, and that takes energy input. Okay, so when you think about this in a net zero sense, you're still going to need a source of energy. If you're getting that energy from burning some kind of a petroleum product, then you've got CO2 that you're releasing. So anyway, it's complicated, but one promising technology that a lot of people work on is this process called photocatalysis. So photocatalysis takes visible light, so it comes in from the sun, and it has an energy, h nu, right? H is Planck's constant, and nu is the wavelength. And the light of varying frequencies can excite the electrons in different valence bands of different atoms. So what I'm showing here, this is a diagram of a nitrogen-doped titanium oxide photocatalyst, okay? And so the energy comes in here and it excites this electron, and this electron comes up to this secondary energy level in the conduction band, and it can be used in processes that need an electron donor to happen. So if you take carbon dioxide and hydrogen and donate some electrons to it, you can split that CO2 apart and make methanol and water. Okay, that has to be further catalyzed with silver, but that's a fairly straightforward process. The other thing that you can do is when you excite the electron out of the valence band, then that can be used to remove electrons from processes that need reduction to occur. So when you split water, that is a reducing process because you're deoxidizing that hydrogen. So you can use photocatalysts to split water into oxygen and hydrogen. Okay, so these are really promising techniques that just use the energy from the sun. So it's pretty clean technology, and there's a lot of neat research being done on this. Now you can also use carbon dioxide as a working fluid. So what is a working fluid? Well, it is used in either a heat engine or a heat pump to have heat either transferred to or from it during a thermodynamic cycle. So a good example of this is refrigeration. So the way your refrigerator works is, here's the inside of the fridge. You want to remove heat from the inside of your fridge to keep your food cold, right? So what happens is that air is passed over an evaporation coil, which contains a working fluid in it. And depending on the properties of that working fluid, that warm air will transfer heat to the working fluid and evaporate it. And the heat transferred from that air will cool it down, okay? And the evaporated fluid then goes into a compressor that compresses it and heats it up. And then it goes into a condenser where there's a phase change back to the liquid phase that again transfers heat, comes back here through the expansion valve and expands and back into the liquid phase. And then you start the process all over again. Okay, so in refrigeration systems, you're going to use some type of a refrigerant that can undergo this phase change at a relatively low temperature. So the boiling point of most typical refrigerants that you use, like an R32 or an R120 or that sort of thing, are typically slightly below 0 Fahrenheit. So you're not going to be using water for this process. But when you start thinking about using these fluids in some kind of a heat pump where you're operating at higher temperatures, for example, in geothermal energy, which we'll talk about in a few weeks, you can start looking at using things like ammonia or carbon dioxide, which have higher boiling points, but they can be used in a heat pump that's operating at those higher temperatures, say, for instance, in a geothermal power plant. So there's a lot of different potential here. Now, why is CO2 advantageous as a working fluid? Well, it has a low viscosity compared to a lot of other fluids. This means that it's easier to pump. It can flow faster, and you're not going to have as much energy loss from friction when it's flowing. It's got a high compressibility. So when you go through the compression cycle, you need to apply less work to it to compress it and heat it up. And it's got a relatively low supercritical pressure, which means that you can actually operate a heat pump with CO2 as a working fluid in the supercritical phase. And what this means is that supercritical CO2 is twice as dense as steam. And so it can carry a lot more heat just because of the product of the density times the specific heat capacity gives you a lot of heat carrying capability. So there's a lot of people looking into using CO2 as a working fluid. It's pretty promising, and we'll see where these things go over the next few years. All right, well, thanks for listening to this lecture on carbon utilization. It was a little bit of a short one, but that's probably okay. And next time we will begin discussing subsurface carbon storage. So thanks for watching, and I'll see you on the next one.